Hey everybody, this is Mrs. Rajewski. Thanks for joining me again. Today we are going to talk about the derivatives of trigonometric functions. But first, let's start off with a little bit of an exploration. So go ahead and get out your graphing calculators. And what I'd like you to do is go ahead and graph the sine of x and the derivative of the sine of x in a trigonometric window on your graphing calculator. So I'm going to pull mine up. I've already got the sine of x ready to go here. Now I'm going to graph the derivative of sine of x. So I'm going to hit Math 8. This is going to pull up the derivative portion of our calculator. And we're going to take the derivative with respect to x of the sine of x. And we are going to let x be x so that our calculator will graph all the different x values instead of just one. Now, I do have to make sure that my calculator is in radians mode, because if I am in degrees mode, it won't graph it at all. There we go, and let's hit graph. Interesting. I'm going to take a snapshot of this. And let's see. Wow. All right, so if the sine of x is this blue line here, what function do you think is the derivative of the sine of x? What does it look like? Let's think about it. What do you guys think? Hopefully, you're looking at that red line and you're thinking, that looks like cosine of x. Kind of looks like it, right? And it's true. If f of x is equal to the sine of x, then the derivative of the sine of x is equal to the cosine of x. Cool. So what does that mean about the derivative of cosine? If the derivative of sine is cosine, what do you think the derivative of cosine is going to be? Remember, derivatives are basically slopes at a point. So when I'm looking at the derivative of sine, we see at 0, the slope of sine is positive. It's just hitting 0 at 0, and it's increasing till we get a maximum value up here, pi over 2, and then it starts decreasing. That's what the slope is doing here. We've got positive, positives, positive. As soon as sine starts to decrease, you notice that cosine starts becoming negative. So if we flip it around, what do you think that cosine's derivative is going to do? Let's check it out. Let's, instead of doing the sine and cosine, we'll do cosine for these ones. Let's see what we get. So that blue line here is now cosine. And when we take the derivative, what does that look like? Well, it doesn't quite look like sine to me. Does it look like sine to you? I mean, a little bit. We see that the midpoint goes through the origin, kind of like how sine does. Remember, up here, sine was our blue line. But instead of increasing from 0, we see that it's decreasing. So what does that look like in this problem? To me, it looks like it's maybe negative sine of x. It's like it's flipped about the x-axis. That's what it appears. So this is a list of all the derivates of the trigonometric functions. So we had our 6 basic trig ratios and their derivatives. So the derivative of sine is, in fact, cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cosecant is negative cosecant times cotangent. The derivative of secant is secant tangent. The derivative of cotangent is negative cosecant squared. So lots to remember. The ones you're going to probably use the most are sine and cosine, and I would say tangent's a close third. Luckily for you, most of these are in the formula packet, so you will not be held accountable necessarily to knowing them, but I hope that you will try. I definitely recommend that you put these on some flashcards and test yourself, especially if you're going further in mathematics. Your calculus teachers are going to expect that you know these. So I wouldn't rely on the formula packet. If you're going to take the AP test, forget about it. You get nothing. So you are going to need to know these frontwards, backwards, sideways, left, and right. And it's going to help you later on when we work with integrals as well. So, but enough about that. I would definitely recommend making flashcards of these bad boys. Here we go. So why does the derivative of sine equal cosine? I'm not going to torture you with drawing graphs of these things. I actually found a pretty cool applet on GeoGebra. So that's what we're going to. So let's check this out. So here I've got this blue line, which is the graph of sine. And as we move along this graph, what I have is this red line, which is the tangent line. So that's going to give you your slope. And what this cool applet does is it plots all the points along the way. So it's going to start graphing, see this y equals f prime of x piece. It's going to start graphing the x comma f prime points. So here I have x is equal to 0, and the slope of this tangent line here is 1. It's a rise over run, so 1 divided by 1 is 1. So that's why they've plotted this point where x is 0, y prime is 1. Okay, so as x increases, you see that your prime is dropping. Well, the reason that that's happening is because as we're moving up along this curve, the slope starts to slowly decrease. It's still a positive slope, don't get me wrong, but it's not as, I hate using the word, but it's not as steep anymore. It's gentling out, right? Until eventually we get up to the tippity top here where our slope is 0. Okay, and then it drops back down, and yes, I'm enjoying myself way too much here. I'm plotting a whole bunch of points. And so all these red dots are representing the slope of the sine graph as x increases or decreases. And as we plot these points, we can actually see that lo and behold, if we plot them like that with it x comma y prime, then we will actually get the graph of cosine. Isn't that cool? Anyways, I thought it was cool. I thought maybe you guys would enjoy that too. So that's why, because when we graph the slopes of sine, it generates the graph of cosine. So let's get to it. I know you guys probably just want to know, how do I solve these darn problems? Well, I can't wait to show you. So check this one out. This looks to me like a product. I can tell that it's a product because I got two pieces that are multiplied together. 2 theta times cosine theta. So this is definitely using the product rule. So I'm going to apply the product rule here, dy d theta, because we're taking the derivative with respect to theta since there's theta in this problem. And here we go. 1d2. So the derivative of cosine is negative sine. So 1d2 plus 2 d1. The derivative of 2 theta is 2. You can treat it just like you treated it with x, so don't freak out if you're like, oh no, new variable? Yes, we've mostly been taking derivatives with x, but we can mix it up a bit. You don't have to be married to x. Okay, so I've got dy d theta is equal to negative 2 theta sine theta plus 2 cosine theta. And if you really want to get wild, you can try and factor that 2 out, but this is a happy answer for me. And we're done. Fabulous. Good job, you guys. All right, so here we go for example number 2. So when I see it like this, you might not immediately recognize it as being a chain rule problem, but it is. Let me show you another way you could write this function. So if we rewrote it like this, f of x is equal to 4 times the tangent of 7x squared. Now, this means the same thing as this. You see I've just moved my square to kind of like the outside of the function. This is really the way we have to enter squared trig ratios into our calculator. So it's good to be able to go back and forth between the two different formats of where you put your square. But I think that when it's in this format, it's a little bit easier to see that you're going to have to use the chain rule here. So that's what we're going to do. We're going to apply the chain rule on this one. So with the chain rule, to take the derivative, I'm going to take my outside function, which is 4 times something squared, and I'm going to leave my inside function the same. So I've got 2 times 4 times the tangent of 7x raised to the power of, well, I have to subtract 1 from my exponent, so raised to the power of 1. But with the chain rule, then what you have to do is you have to multiply by the derivative of your inside function. So my inside function is the tangent of 7x. So the derivative of tangent is secant squared. So we're going to multiply it by secant squared. And it's not going to be secant squared of x. It's going to be secant squared of 7x because that's the inside function. You have to keep that part the same. But you're not done yet because we're still trying to take the derivative of the tangent of 7x. And while it is secant squared of 7x, we have to multiply by the derivative of what's inside. Again, another chain. So the derivative of 7x is 7. And now we have finally taken the derivative of everything that's inside. Now we got to simplify it. So let's do that. 2 times 4 times 7 is 56. Then we have times the tangent of 7x. We could put parentheses around it if you like. Secant squared 7x. And, you know, we already multiplied that 7 over here to get the 56. And this is a happy answer. I'm totally satisfied here, but you could simplify it more. And I just caution you that the number one area that students will make mistakes in calculus is not on the calculus part, it's on the algebra part. So you want to be careful. I happen to know that tangent is really sine over cosine. So that's like saying the sine of 7x divided by the cosine of 7x. And I know secant squared of 7x is the same as 1 over cosine squared of 7x because it's a reciprocal function for cosine. And I can simplify a bit more, just a bit. And this is going to give me 56 times the sine of 7x, all divided by cosine cubed 7x. If for some reason the directions asked you to write it in terms of sine and cosine, this would be the answer that you would want to get. So I just wanted to take it to this place just so you could see, you know, like I said, this is a happy answer for me, but if I asked you on an exam to write it in terms of sines and cosines, this would be the solution I would be looking for. If I didn't stipulate, this is correct, and you should stop there so you don't accidentally make an error that you don't need to. Moving on. Here we go. Example number 3. So I've got y is equal to the cosecant of 2 theta. Now, when I see this, I'm kind of like, well, I don't really know off the top of my head what cosecant 2 theta is. Maybe, I don't know. I do, but let's just pretend I didn't. Then maybe what I would want to do is change it to something I do know, such as, well, I know that cosecant is the reciprocal of sine. And if I saw it like this, then hopefully I would say, at least I know how to use the quotient rule. Okay, so let's try the quotient rule. The quotient rule says low d high, so low d high, the derivative of what's on top, so the derivative of 1 is 0, minus high d low, the derivative of what's below. Derivative of sine is cosine. And this is a chain rule cosine because I have something in my argument. So I'm going to have to multiply by the derivative of what's inside, which is 2. Low d high minus high d low all over the square of what's below. Okay, sweet. So, all right, sine of 2 theta times 0 is 0. And I've got negative 1 times the cosine of 2 theta times 2. That's going to be negative 2 cosine 2 theta, all divided by sine squared of 2 theta. And we're done. Now you might say, I'm not really the biggest fan of the quotient rule, Mrs. Rajewski. What if there was another way? Well, there absolutely is. I already showed you on the first slides that the derivative of cosecant is negative cosecant times cotangent. So you can actually apply that rule. So let's go ahead and do that. So we've got y prime is equal to, the derivative of cosecant is negative cosecant. Remember, your argument is 2 theta. You're going to have to multiply by the derivative of what's inside. Times cotangent 2 theta. Okay, that's the formula that we're using for the rule. Times the derivative of what's inside, which is 2. This is not a product rule problem. This was the original function that we had to take the derivative of. Its derivative contains 2 pieces, but you're only applying the derivative of cosecant. You don't have to do the product rule on this. So that's definitely something I've seen students be confused about. Then we can tidy this up. I've got a negative and a 2. Cosecant is really 1 over sine. And then, of course, our argument stays 2 theta. And cotangent is really cosine over sine. That's another sine, so I'll just put my square here. Oh, what? Oh, it's the same thing. So depending on which way you want to go, if you prefer working with sine and cosine and just using all the other different rules that you have, that's definitely a strategy. Or if you have your formulas memorized, then you can use those too. It's usually faster. So there's that. Moving along. Here we go. Example number 4. So here, this is a fun one. So I noticed that g of x is a square root function. And if you know me, and I hope you do, then you know I much prefer working with square roots as rational exponents instead of as square roots. I find that they're easier to work with algebraically. So I'm actually going to rewrite this so that I have the secant of 3x divided by 2 all raised to the 1/2 power. Now, when you see it like this, it becomes fairly obvious you got a chain rule situation. This is going to be multiple chain rules because not only do we have something raised to the 1/2 power, but we have secant of something. So we got 2 somethings here. So multiple chains. And away we go. So to take the derivative, first I'm going to apply the power rule. So I'm going to multiply by 1/2 to the front. Everything else stays the same. And I subtract 1 from my exponent. When I subtract 1 from my exponent, I'm going to use a clever one, which is really 2 divided by 2, so that I have 1/2 minus 2/2, which is negative 1/2. But you're not done yet because now you've got to take the derivative of what's inside. What's inside is secant 3x divided by 2. So the derivative of secant is secant tangent. So we're going to multiply this by secant tangent. Keep what's inside the same. Then you have to multiply by the derivative of what's inside that. So inside of the secant, was 3x divided by 2. So we're going to multiply by the derivative of 3x divided by 2, which is just 3/2. Wowzers. Okay, so now it's time to simplify. Goodness me. Well, the easiest things I think to multiply are 1/2 and 3/2. Yeah, the fractions. So let's start with those. 1 times 3 is 3, and 2 times 2 is 4. Now I have the secant raised to the power of negative 1/2 and a secant that's raised to the power of 1. I can make that a fancy one, so we could actually make it to the power of 2/2. And since these are the same base, different exponents, we can just add the exponents together. So that's going to give me the secant of 3x divided by 2, all raised to the power of 1/2. So again, I saw that they both were secants of 3x divided by 2's. This one had a power of 1/2 on it. This one had a power of 1, which I wrote it as 2/2. And then I just added them together, because when your bases are the same, you can add your exponents. So negative 1/2 plus 2/2 is positive 1/2. Now we still have this tangent over here. Good gravy. So that's going to be the tangent of 3x divided by 2. And I think I got all my pieces, right? Because I multiplied the 1/2 and the 3/2 together. So let's just make this look a little prettier. I mean, I don't really think it's going to be gorgeous, but we have this power of 1/2, which we know is really a square root. So let's say we've got 3 times the tangent of 3x divided by 2 times the square root of the secant of 3x divided by 2. And the whole thing is divided by 4. Wow. That's actually kind of beautiful at the end there, if you can appreciate it, which I hope you can. I can. Alrighty. So let's go on to example number 5. Number 5, we're there already? This is so much fun. Okay, so example number 5 asks you to find the equation of the tangent to y is equal to the cosine of 2 theta at x equals pi over 3. Okay, so this is an equation. I'm not just looking for the derivative. I need to use the derivative to write an equation. This is really why the derivative is so important, one of the reasons. So when I write equations, I like to use the point slope formula. So point slope formula says y minus y sub 1 is equal to your slope times x minus your x sub 1. Now, when you're writing the equation, this y without the subscript and this x without the subscript, they're going to remain y's and x's. So you're not going to replace those with anything. But you are going to replace all these other pieces. So we're going to need to find our y sub 1. We're going to need to find our slope. And we're going to need to figure out what our x sub 1 is. Luckily, they've given us our x sub 1. This is it right here. This is our x sub 1. And we're going to use that to find all these other pieces. So if our x value is pi over 3, then the y value, well, it's given to us right up here, right? Then y is equal to the cosine of 2 times, well, that should be an x. Oh, let's make it an x now so we can substitute it in there. Pi over 3. I'm going to have to change that in my flip chart. Okay, so we're going to multiply those together. 2 times pi over 3 is 2 pi over 3. When the cosine value at 2 pi over 3 is negative 1/2. That's over there in quadrant 2, right? We have our pi over 3 over here. 2 pi over 3, that is. So that means that we've got the point pi over 3, comma, negative 1/2. This is our x sub 1. This is our y sub 1. So we've got this to substitute in and this to substitute in. The last thing we need to find is our slope. Luckily for us, we know that our derivative is a slope generating equation. So if I want to generate a slope, I'm going to need the derivative. So we're going to take the derivative of the cosine of 2x, not 2 theta, goodness me. So the derivative of cosine is negative sine. Keep your angle the same, so that'll be 2x, and then multiply it by the derivative of your argument. So the derivative of 2x is 2. Now, when x is equal to pi over 3, what's the derivative there? Well, y prime is equal to negative 2 sine of 2 pi over 3. Now, at 2 pi over 3, sine is the square root of 3 over 2. But don't forget, that's getting multiplied by this negative 2 as well. And that's great because those 2's are going to cancel out. And we're going to be left with y prime is equal to negative radical 3. And this is the slope of our tangent. And this question is just asking us to find the equation of the tangent. So that's fantastic. Let's do it. Here we go. So for the tangent line, we've got y minus our y sub 1, which we have right here, is negative 1/2, is equal to our slope, which we found is negative rad 3, times x minus our x sub 1, which our x sub 1 was pi over 3. Two negatives make a positive. And I'm going to solve this for y. So I'm going to subtract that 1/2 over to the other side. Now, on my lab and mastering, they're probably going to want you to do the distributive property and collect like terms if you can, or just do the distributive property and then have your final answer. But I am a very happy Mrs. Drieski with this solution right here for your tangent line. You can stop right there for me. If somehow it marks you wrong on my lab and mastering, just shoot me an email and I will make sure I give you the points back. Now, sometimes you'll be asked to find the normal line. Now, the normal line is actually the line that's perpendicular to the point. So tangent is giving you the slope right at the point. This is asking you for the line that is perpendicular to that tangent line. So if your slope is negative square root of 3, the normal slope is the opposite reciprocal. Okay, so we use this like upside down T as like the representation for perpendicular. So your normal slope is going to be the opposite. So instead of being negative, it will be positive. Reciprocal. So instead of being square root of 3 over 1, it's going to be 1 over the square root of 3. And that's also the same. Goodness, that equal sign was terrible. That's the same as the square root of 3 over 3. So if we're going to write a normal line, which by the way, this question does not ask us to do, I'm just being an overachiever. If they ask us for the normal line, it's actually the same line, but instead of writing negative radical 3 for your slope, you're going to write square root of 3 over 3 for your slope. And then, like I said, if they want you to have it in like a nicer slope-intercept form, you'll actually use the distributive property then and simplify. But for me, this is a lovely normal slope equation, which again, this question did not ask us to do. I just couldn't help myself. And I figured that eventually at some point, you're going to probably come across a problem that asks you for the normal, and now you'll know how to do it. And you won't have to wait to that point in our lessons, which will be coming shortly, for you to do so. Okay, so tangent line, normal line. Okay, we are nearly there, my darlings. But first, inverse trig functions. Yes, you can take the derivative of inverse trig as well. So don't be scared. I know that these look pretty crazy, and we are actually going to do proofs of where these things come from coming up shortly. But I haven't taught you implicit differentiation, and we're going to need to utilize that to do the proofs. So since we're not there yet, we're walking before we run. Just trust me that these are accurate, and I will show you where these come from eventually. And if you just can't contain your curiosity, go check your textbook. The proofs are all in there too. So remember, arc sine is the same as saying the inverse sine, right? Arc cosine is like saying your inverse cosine. And arctan is like saying your inverse tangent. So if we take the derivative of our inverse functions, we get this kind of interesting result, and this is going to help us later. And they do have limited domains for most of them, so just be aware. Remember, when we take an inverse, we're flipping our x and our y values. So where sine is normally having a range in between -1 and +1, inverse sine is going to have that be its domain, and so on with cosine and tangent. So just be aware of that when you're calculating these. Okay, again, this would be another thing that I would definitely recommend that you put on your flashcards, especially if you're going to take the AP test, because you absolutely have to know these frontwards, backwards, and sideways. So here we go. For this problem, we're going to differentiate with respect to x or theta. Looks like we have theta in the problem, but I must have changed this problem and not changed my theta here. So let's go ahead and make that a theta. Okay, so when we take the derivative, this is a chain rule problem because I do have a function on the inside of the argument here. So we're going to have to be careful and make sure that we don't miss the chain. So let's say f prime of theta is equal to, now the formula to calculate the derivative is this 1 divided by 1 plus x squared. So that's what we're going to use. We're going to use 1 divided by 1 plus, but obviously we don't have an x squared. We have an argument here that's theta divided by 2. So that's going to be theta divided by 2 squared. And then we have to multiply by the derivative of what's inside. So we're going to multiply by the derivative of a half theta, which is just a half. All right, so now we're going to simplify. 1/2 times 1 is 1/2. I have 1 plus theta squared divided by 4. I could have a multiplying by 4 party where I multiply the top and the bottom by 4, which is probably the easiest thing for me to do. So let's go ahead and do that. Why would I do that? Just so I'm not working with crazy fractions in my denominator over here. So I'm going to multiply the top and bottom by 4. 4 times 1/2 is 2. 4 times 1 is 4. And 4 times theta squared over 4 is theta squared. Final answer. I know. It looked like with all of these formulas, like, oh my gosh, this is going to be crazy. What are we doing here? But it's actually not so bad. You're just substituting in. So whatever we had in this position for our argument, that's what's getting squared here. And just don't forget that you have to multiply by the derivative of what's inside if you've got a chain rule situation. Okay, this is our last one, I absolutely promise. And well, gosh, you guys, you know that I love the natural base. I'm a real big fan. And so when we get a chance to work with that, you know I'm going to. This one is a product rule. You can see the two pieces here. So we definitely have some product rule that we're going to get to do. However, you see this 2x? Oh, that's a sneaky chain. So watch out for that sneaky chain. We got to take care of that. So let's do it. Here we go with our derivative. Y prime is equal to, this is the product rule, so we're going to apply the product rule, 1d2. So the derivative of arc sine is 1 divided by the square root of 1 minus your x, or in this case your argument, 2x squared. Okay, so that's 1d2. Don't forget the sneaky chain rule. The derivative of 2x is 2. 1d2 plus 2 d1. Well, the derivative of e to the power of x is itself e to the power of x. Oh, the transcendentals. And then we just have to simplify a bit. So I've got y prime is equal to, let's see, e to the x times 1 times 2 is 2e to the x, all divided by the square root of 1 minus, well, 2x squared is really 4x squared, plus the arc sine of 2x times e to the x. And actually, most of the time, I actually prefer to put my e to the x first. So that's what I'm going to do here. Doesn't take me much time. And we're pretty much done. I suppose you could factor out e to the x, but we'd be pretty much just showing off to do that here. So we're done. And if you were like, holy smokes, where did she get this square root thing from? How did she go from there to there? Again, I'm just simply using our formulas for the derivative. So the derivative for arc sine is 1 divided by 1 minus x squared. And that x is whatever's inside your argument there. So in that problem, our argument was 2x. So I just used the 2x for this x right here. See? So hopefully that made sense. When we get together and have our next meeting, you can definitely ask me about it if you have more questions. But until then, please go ahead and try the MyLab of Mastering Day 7 homework, the derivatives of trigonometry. And, for some extra practice, or if you're not working with MyLab of Mastering, from our textbook, these are the best problems for you to try. I hope you guys are doing well, and I miss you tons. Take care until next time. Bye-bye.